The ideal gas law helps us describe the behavior of gases. The ideal gas law uses all four properties used to describe a gas. So we have pressure, volume, the amount, then we have a gas constant, which I'll write in a minute, and the temperature. So it's a gas law that contains all four of the properties. Now R is the ideal gas constant, so that means it always is going to have the same number. And the one we're going to use is 0.0821. The units are liters times atmospheres over moles times Kelvin. Now, it's important that you pay attention to the units for R that you're using, because these units are the same units you have to use for the properties in your problem. So if you look at the gas constant, it has all four properties in its units. So liters right there would be for volume. Atmospheres is a unit for pressure. That's a P. The amount, N, is moles. And the temperature, as with all gas laws, is in Kelvin. So the important thing here is when we're working a problem and setting it up, my units have to match the units in the gas constant. So I have three problems here to kind of work through these different units, like what to do, how do we recognize there's different units. So let's take a look at this first one. It says how many moles of gas are contained in a human breath that occupies 4.5 liters and has a pressure of 747 milligrams of mercury at 37 degrees Celsius. So let's kind of go through and see what we're given. So here the question, what we're trying to find is moles. How many moles? So N is the thing I'm not going to know because that's what I have to. That's what I'm trying to solve for. And then if I keep reading, it occupies a 0.45 liters. Okay, liters is my volume, and liters is okay because I have liters up here. So I don't have to do anything to that. It has a pressure of 747 milligrams. So here's my pressure. But if you look, this is in millimeters of mercury. I don't know what I said, milligrams. I'm thinking ahead. Sorry, millimeters of mercury. And if I look here, I have to have atmospheres as my pressure. So I'm going to have to convert this millimeters of mercury into atmospheres. And then finally, I also have a temperature here, and it's very common. The temperature is in degrees Celsius, which is very common, and I have to convert it into Kelvin. So before I can even use the gas law, I have to make some conversions. So let's try. I'm going to start over here. So I know I need to do pressure. So the pressure is 747 millimeters of mercury. And I'm going to erase this so I can write there. To convert it, let's see, there are 760 millimeters of mercury in 1 atmosphere. So I'm going to set it up so the units of millimeters of mercury will cancel. And I'll write that conversion factor up here in case you need it in the future. It would also be in your textbook, or you could even look online. So that's the relationship between millimeters of mercury and atmospheres. So get my calculator out. And so it's going to be 747 divided by 760. And so to 3 significant figures, I get 0.983 atmospheres. Okay, so now I have my units in atmospheres, which is what I need to solve this problem. But I also needed to convert degrees Celsius to Kelvin. So I'm going to add 273 to 37, so I have 310 Kelvin. Okay, so now I think I'm ready to set this problem up, and I'm just going to kind of block this off so I can do my work. So I say PV equals nRT, so PV equals nRT. So P is 0.983 atmospheres. Volume is 0.45 liters. That's going to equal N, which remember I said I didn't know, and then I'm multiplying 0.0821. I have all these units here, and I'm multiplying that by 310 Kelvin. If you're watching units at this point right now, Kelvin cancels out. So I have 0.983 times 0.45. And I'm going to move it over here further. I have 0.44235. The units now would be atmosphere liters if you're keeping track of that. I don't need to have a parentheses. That equals N, and then I'm going to multiply 0.0821 times 310, and I get here, this is times 25.451. It would have still weird units, liter atmospheres over moles. The Kelvin already canceled. And now I'm going to divide, and I've kind of worked my way into the corner of this page, and I apologize for that. So now I'm going to divide, so I would say 0.44235 atmosphere liters divided by 25.451. And so now if you're following with your units, you'll notice liters cancel and atmospheres cancel, and all I have is moles, which is good. So let me divide these two things. I get 0.44235. I'm dividing it by 25.451, and I get 0.01738 moles. That's what I get up here. So I think to two significant figures because of the 0.45 liters. So N equals 0.017 moles, and that's my answer right there. So remember, in this problem, how we began is we started by looking at the units, and to begin this problem, which isn't always the case, but for this problem, because millimeters of mercury did not match atmospheres and degrees Celsius did not match Kelvin, before I plugged it in, I had to change those units. So let's try another one. Try to think through again. I'm giving several different things. This one says how many moles of air. So again, as you read your problem, and you can write it out if you want. So how many moles? So I'm looking for N. How many moles of air are present in the lungs if they occupy a volume? So here's my V at a degree Celsius. So here's my T, and a pressure of millimeters of mercury. So I identify this, and I think, well, I'm going to use the ideal gas law because I have all my variables here. So PV equals nRT. And I have to check with R and make sure that my units are going to be able to cancel with R. So R is 0.0821. It's a constant. Liter, atmospheres, moles, Kelvin. So let's check out our units. So moles is what I'm calculating here, so I'm good. Okay, this has liters, and this has liters, so I don't need to convert that. Okay, this has degrees Celsius, and this, oops, I didn't write the Kelvin. Sorry. Sometimes my brain gets ahead of me. All right, so this has degrees Celsius and this has Kelvin. So I need to convert that. I'm going to go ahead and write it down here. I need to go 37 degrees C plus 273. That is 310 Kelvin. Okay, I got that. And then I also have pressure, and here the pressure is millimeters of mercury, but this one is atmospheres, so I need to convert that, reminding myself that 1 atmosphere equals 760 millimeters of mercury. That's my conversion factor. So let's change that one before we get started. So that's 740 millimeters of mercury. I'm going to use my conversion factor, so the 760 millimeters of mercury goes on the bottom, the atmosphere goes on the top, so the units cancel. So it's going to be 740 divided by 760, and I get 0.97368. So just, I guess I'll go to 3. I don't know. I'm looking back at the problem I wrote. Probably I could just go to 2 the 740, but I'm going to go ahead and go to 3 till the end. 0.974 atmospheres. Okay, so now I think I'm ready to solve it. So I say PV equals nRT. Pressure in atmospheres is 0.974 atmospheres. The volume was given at 5.0 liters. I'm looking for N. R is always a constant. And then times temperature is 310 Kelvin. My temperatures cancel. So 0.974 times 5, I get 4.87 atmospheres and liters over here, and that equals N. 0.0821 times 310, I get 25.451 liter atmospheres moles. Then to solve for N, I'm going to divide. Okay. The liters and atmospheres both cancel, and I just have moles. So that equals N. So if I take 4.87 and divide it by 25.451, I get 0.19. Oh, and I think I can do 2 significant figures, because if I look up there, moles. Okay, now it asks me, the second question says how many molecules does this correspond to? Okay, so let me take it to the next page. I need to... Okay, so let me take it. I had this other problem already set up, so hold on. Pause this. Okay, so I added an extra slide here so we could finish that problem. So if you look back, it says, I first ask you how many moles, and we calculated that the number of moles is 0.19. But then the second part of that question was how many molecules, which is kind of a throwback for us because it was several chapters ago that we talked about how you convert moles into molecules. So this problem would help you or jog your memory, make you refresh your memory that we know that 1 mole of anything contains 6.02 times 10 to the 23 units. In our case, we're looking for molecules. So in order to go from moles To molecules, we would put the 1 mole on the bottom and good old Avogadro's number on the top. So if we take, and let's see what that equals. We take 0.19 and multiply by 6.023, or 6.02. 23 is one more significant figure, times 10 to the 23rd. And I get to two significant figures, 1.1 times 10 to the 23rd molecules. So in this question, while we started out using the gas law, once they started asking about molecules, it threw us into the next thing where we had to recall Avogadro's number. Okay, one more problem with ideal gas law, and this gave us something else a little bit different, but let's go ahead and read through it and see what we discover. So it says if a cylinder contains 10 grams, okay, so grams, they're giving me a mass of carbon dioxide in a 10 liter, so liter is my volume, at 325 Kelvin, that is my temperature, and they're asking me to find pressure. So looking at this, I have this gas, and I see that I have three variables that describe a gas: pressure, volume, and temperature. So I think to myself, I'm going to use the ideal gas law. So the ideal gas law is PV equals nRT. Now R is the gas constant, and the reason I like to think about it when I'm using the ideal gas law is I always want to check out my units before I get going. So I look here. Now first of all, there's mass. Okay, there is no mass in the ideal gas law, but what I do know is that mass can be converted into moles. So I'm going to have to convert mass into moles using the molar mass. So I have to do that first. It's important. They told me CO2, so I'm going to have to get the molar mass of CO2. Now volume is in liters, and check. Liters are fine. Temperature's already in Kelvin. That's good. And P is pressure, is what I'm going to try to find. So I will find my pressure in atmospheres. So the first thing I'm going to do is convert grams to moles. And so to do that, I need the molar mass of CO2. So to do that, I use my periodic table, and carbon has a molar mass of 12.01. I only have one carbon, so that's good. Oxygen has a molar mass of 16, but I have two of them, so that gives me 32. So the molar mass is 44.01 grams per mole. So to convert into moles, which I have to do because I need moles for the ideal gas law, I say 10 grams. I want to put the grams on the bottom so they cancel. The 1 mole on the top. So I'm going to take 10 grams and divide it by 44.01. And I get 0.227 moles. Okay, so now I have moles. So I have everything I need to do the problem. So PV equals nRT. Pressure is what I don't know. The volume is 10.0 liters. The N I just calculated is 0.227 moles times R and then times temperature, which is 3 325 Kelvin. If you're following along with units, the moles cancel, the kelvins cancel, and let's multiply those numbers. 0.227 times 0.0821 times 325, and I get 6.0, I won't round it yet too much, 569, and it would have units of liter atmospheres. The moles and Kelvin canceled. So it looks like that. I'm looking for P. So to get P all by itself, I'm going to divide. So P equals 6.0569 liter atmospheres divided by 10 liters. The liters are going to cancel. And so then I get 0.60569 atmospheres. Let's look up at significant figures. I think 3 seems reasonable for what we were given. So I would say 0.606 atmospheres. So then in summary, in this case, as we look through, they gave me the mass of the carbon dioxide, but to use Avogadro's, to use the ideal gas law, I need to have moles. So I first had to use the molar mass of carbon dioxide to convert to moles, and then once I did that, I could go ahead and plug into the ideal gas law.